All right, so this is section 11.6, video number 2. In video number 1, we talked about the idea of absolute conversions, as well as started to look at some examples of the ratio test. So we'll continue on with our examples. Example number 3, see it has a little asterisk by it there, and there's a reason for that. This is not exactly the easiest one, and when you kind of get to the end of it, there's something you have to recognize, which I kind of enjoy, so that's why I'm doing it. Let's go ahead and start with the fact that, first of all, what you have is an iterated function, n to the n power, over a factorial, n factorial. Remember, the iterated functions are probably, of the ones that we look at, the ones that grow the fastest. So you would expect, since the numerator is going to grow faster than the denominator, even though they both grow extremely fast, the top is going to grow faster. So you would expect this one to probably be divergent. So let's go ahead and see by using the ratio test if that is true. So let's start off by taking the limit as n goes to infinity. And remember, this is the n plus 1 term, absolute value of n plus 1 raised to the n plus 1. Again, notation is important there. Divided by n plus 1 factorial. Then you have to divide that by the n term, which is the same as multiplying by the reciprocal of the original, which is going to be n factorial over n to the n power. All right, so let's just kind of reorder. Limit as n goes to infinity. Absolute value, n plus 1 to the n plus 1 over n to the n, times n factorial over n plus 1 factorial, kind of putting the factorials together and then the other two pieces together. So in this case, the factorials are actually going to be the easier part to simplify. So we'll have, I'm just going to leave the other one alone for right now. It's n plus 1 to the n plus 1 over n to the n, and then n factorial over n plus 1 factorial. Remember that n plus 1 factorial is the same thing as n plus 1 times n factorial. So you're just going to be left with a 1 over n plus 1 out of that. Okay, and at this point, it doesn't look like that has helped very much, but it will. So let's look at the left fraction there. We're going to try and simplify that one. Again, this is where the algebra kicks in. So n plus 1 to the n plus 1 can be rewritten as n plus 1 to the n times n plus 1 to the first power. I'm not going to write the first power, but that's what it is. So again, your n plus 1s would be your base, and then you would add the exponents if you recombine them. And then you still have over n to the n. And this is where the simplification of the factorial piece helps, because now I've got a 1 over n plus 1. Well, hopefully you can see now that the n plus 1s are going to divide out. Those are going to go away, which is nice. Because what it leaves us with is the limit as n goes to infinity, absolute value of n plus 1 to the n over n to the n. Again, algebraic properties. I have two things which are being raised to the same exponent. So I can combine those two things and raise the whole thing to that exponent. So we'll have the limit as n goes to infinity of the absolute value of n plus 1 over n, all raised to the n power. And you might still be looking at that and thinking, how does that help? Well, let's simplify what's inside that parentheses. We've got n plus 1 over n. I can separate each one of those pieces on top of the n denominator, and what we get finally is the limit as n goes to infinity of 1 plus 1 over n, all raised to the n power. Now, if you don't actually recognize what that is, that's okay, because a lot of people aren't really taught this specifically. But the limit as n goes to infinity of 1 plus 1 over n raised to the n power is actually the definition of the number e. Okay, and we're used to seeing e with exponentials and exponential growth and all that kind of stuff. The approximate value is 2.71, and then so on, it goes on. But that's the actual definition. That's how you find e, is the limit as n goes to infinity of the not absolute value of 1 plus 1 over n, all raised to the nth power. And since e is a number which is definitely greater than 1, we know that this one is divergent. All right, just kind of a cool example. All right, determine the convergence or divergence of the sum of 3 over n to the fourth. And just because we're in this section does not mean we have to use the ratio test or even the root test, which we haven't talked about yet. If you recognize this one is so much easier to do if you just recognize it as a p-series. Remember, technically that 3 could be brought out to the front and then you would have 1 over n to the fourth. This would just be a p-series where p is 4. So p is 4. For a p-series to be convergent, that just has to be bigger than 1, which it definitely is, and therefore this would be a convergent series. So again, excuse me, just because we're in that specific section does not necessarily mean you have to use that specific criteria. If you can use something simpler, do it. All right. Number 5, let's determine the convergence or divergence of n plus 3 over n factorial. Again, hypothesis should say, okay, the numerator is linear, where the denominator is a factorial. This should definitely converge. The denominator will grow really, really fast compared to the numerator. Let's show it. Is there any other test that we can use? Considering we have that factorial, probably not. So let's go ahead and use our ratio test. So we'll have the limit as n goes to infinity of the n plus 1, absolute value of the n plus 1 term, which will be n plus 1 plus 3 over n plus 1 factorial, times the reciprocal of the n term, which is what we get there. Now I'm going to stop the rearranging and simplifying and just go to the simplifying at this point. So we're going to get the limit as n goes to infinity. The n factorial over n plus 1 factorial will leave me with an n plus 1 in the denominator. On the numerator, I've still got an n plus 1 plus 3, which is n plus 4. And then unfortunately in the denominator, I also still have an n plus 3. So I'm going to have to multiply that together with that one. I don't really have to distribute everything out. Just know that I've got a polynomial over a polynomial at this point, and what we have is an n divided by an n squared as far as our dominant terms are concerned, so the denominator will grow faster than the numerator as n goes to infinity, which means that this one will approach 0, which is definitely less than 1, and it is important to state that part in every problem. Therefore, this one is convergent. Once you get the hang of the algebra and how to simplify, most of these are going to be pretty quick. Not all, but most. Excuse me. Okay, number 6, determine the convergence or divergence. Once again, what we have here is we have an exponential on top of a factorial. So the factorial should grow fast enough that makes this one convergent. Let's show it. The limit as n goes to infinity of the absolute value of the 3 to the n plus 1 divided by n plus 1 factorial times the reciprocal, so n factorial over 3 to the n. Simplifying, limit as n approaches infinity. So the 3 to the n plus 1 over 3 to the n is going to simplify to 3 on top. The n factorial over n plus 1 factorial will leave me with an n plus 1 in the denominator. As n goes to infinity, that one approaches 0, which is less than 1, and therefore convergent. Again, showing the work, showing the process is probably the most important part, because you should be able to look at that one to determine it was convergent anyway. All right. Let's see here. We've got n to the negative 2 over times e to the n. So you could rewrite that one, first of all, as e to the n over n squared, just so you can get a better idea that this is probably going to be divergent because the top is exponential, the bottom is polynomial. Exponentials will grow much faster, so it should be divergent. Do you have to use this specific test? Yeah, I mean, probably other ways you could do it. There's no reason in this case not to use the ratio test. I think it's just as easy as anything else, so let's try it. Limit as n goes to infinity, absolute value, e to the n plus 1 over n plus 1 squared times the reciprocal, n squared over e to the n. Let's simplify. So we've got e to the n plus 1 over e to the n, which will leave an e on the top. And then the n squared over n plus 1 squared pretty much has to stay. Oops, that should be not to the n power, it should be 2. So the numerator and denominator are going to have the same growth rate of n squared, and it looks like we are going to have a limit here of e, which means that that is greater than 1 and therefore divergent. So again, just be careful on your algebra and you will be successful on most of these problems. All right, number 8. Let's see, we've got a polynomial over a polynomial, but I've also got an exponential in the denominator, which is the dominant term. So this one looks like it should probably be convergent. Let's double check to make sure. So we'll have the limit as n goes to infinity of, let's see here, absolute value of the n plus 1 term is going to be n plus 2 squared over n plus 1, 2 to the n plus 1 times the reciprocal of the original. All right, let's see what we can simplify, if much. So I know I can simplify the 2 part for sure. So we'll have a 2 to the n over 2 to the n plus 1. That'll leave us with a 2 in the denominator. Everything else looks like it's polynomials here. I've got an n plus 1 and an n plus 1 squared, which will really just give me an n plus 1 cubed. And then on the top, it looks like I've got, oops, I'm erasing too much here. On the top, it looks like I've got an n plus 2 squared times an n. So it looks like our highest powers in the numerator and denominator are both going to be n cubed. So your leading coefficients here are going to end up giving us 1/2 because of that 2 in the denominator. 1/2 is less than 1 and therefore convergent. All right, I believe that we have one more example. And then we're going to move on to the root test, which we'll come back with another video to do. So let's take a look at this last example here. Got a bunch of stuff going on here with exponentials, factorials, polynomials, all kinds of stuff. This is definitely a good one to try and use the ratio test. So the limit n goes to infinity of absolute value 4 to the n plus 1, n plus 1 factorial divided by n plus 1, n plus 5 factorial, oops, don't want to end that yet, times the reciprocal of the original, n plus 4 factorial, 4 to the n factorial. Wow, okay. A lot of stuff going on here. Let's simplify. So the easiest thing to simplify so far looks like the 4 part. That's just going to give me a 4 on the top. Let's see, what can we get rid of here? So I don't know how you want to do this. There's multiple ways you could go about doing this. The n plus 5 factorial and the n plus 4 factorial. So that's going to be n plus 5 factorial is n plus 5 times n plus 4 factorial. So this part on the denominator is going to get rid of that factorial along with the whole n plus 1 factorial. That leaves us just with an n plus 5 in the denominator. Okay, that's from the part that I just took care of there. Let's see. Well, next part's actually kind of nice. Let's think about this. So n plus 1 factorial is n plus 1 times n factorial. Well, look what you have in the denominator. I have n plus 1 and n factorial. That's going to get rid of that whole thing, which really just leaves us with an extra n in the numerator. So that actually simplified quite nicely. The growth rates on the numerator and denominator here are the same, which is going to end up giving us a limit of 4 over 1 or 4. 4 is definitely bigger than 1, excuse me, and therefore this one is divergent. All right, and if what it says at the bottom of this page is if you had done the number 4 by not realizing that it was a p-series, you would have gotten an inconclusive result, and we would have had to have tried some other method. So we take a look at it and figured out it was a p-series pretty quickly. If you had done it using the ratio test, you would have gotten 1, which means that it would have been inconclusive. All right, that's enough for this video. We're going to come back with another video and start the root test.